Imagine a place where a satellite can circle the Earth in 90 minutes. Where a tourist on vacation wakes up and takes in their view from a hotel room in space. Or where a speck of paint becomes a lethal weapon, able to blow a hole in the side of a spacecraft. These are the realities of Earth orbit, the gateway to the solar system. And it's the turf of astronauts, space junk, and the ultimate thrill seeker. Journey out with us to the edge of space. In the not-so-distant future, a human will board a rocket, sit on an open platform, and launch 120 miles straight up into Earth orbit. Dressed in a high-tech spacesuit, he'll peer through a quartz-coated visor and take in an unparalleled view.
Being in low Earth orbit is spectacular. When you look up, you see the inky blackness of outer space and the stars shining even in daytime. Looking down, you see the hazy blue glow of this gigantic ocean right underneath your feet.
This observer is a space diver, a new breed of ultimate thrill junkie. And as he unhooks from his safety harness and stands at the edge of space, he takes one last look out to the universe and leaps, speeding towards Earth below. Space diving is one of many futuristic ideas planned for Earth orbit. The zone of space that surrounds Earth and begins 120 miles above sea level. It's the home to satellites and the space station. And if orbital outfitters have their way, the ultimate extreme sport, skydiving from space. Earth orbit is a window to the universe, and perhaps will become an extension of Earth itself for industry, exploration, and fun. But the environment in Earth orbit is very different from home. Oxygen ceases to exist here, and the atmosphere that provides a protective shield around Earth disappears. Cosmic threats lurk for those who dare explore here.
We forget that outer space is dangerous. We forget that in outer space we have cosmic radiation, we have solar flares, we have meteors, we have space debris. It's an obstacle course being out there in outer space.
Like free-fall skydiving junkies who leap out of planes and speed towards Earth, space diving might seem like the ultimate thrill. But its idea is based on very serious intentions. Dr. Jonathan Clark, a Navy flight surgeon and former Navy high-altitude parachutist, is one person behind the space diver concept, but for very personal reasons.
I was assigned to NASA to work on space operations. And then my wife was an astronaut.
Columbia, Houston, UHF comm check.
She died on the Columbia mission in 2003.
While military pilots routinely eject safely from imperiled aircraft, currently, there is no evacuation procedure for astronauts to eject from a spacecraft during a catastrophic event.
About 1% of the time, we have a major booster rocket failure or a catastrophe in outer space.
Perhaps the skydiver spacesuit will become a new safety device for astronauts to use on missions. And its first test is a 160,000-foot jump. To survive re-entry, the skydiver spacesuit has many critical features. a protective one-piece jumpsuit that insulates from the negative 40-degree Fahrenheit space environment to the 464-degree heat generated from re-entry. Small gas jets on each glove to orient and direct the body during weightlessness. A full closed-loop oxygen system that will recirculate and remove carbon dioxide for the 10-minute trip home. A drogue parachute to stabilize the space diver as they come closer to Earth. And a traditional parachute that will deploy at 3,000 feet for a safe landing. And the journey will be spectacular. In the first 2 minutes of the jump, the space diver will reach speeds of 2,500 miles per hour while in free fall. Atmospheric drag will heat the spacesuit to 474 degrees Fahrenheit and slow the space diver to terminal velocity, 120 miles per hour. As his drogue parachute breaks free at 7 minutes, he will begin to slow down. Finally, at 3,000 feet, a regular parachute deploys, and the space diver lands safely on the ground.
It will be cinematic.
Chris Gillum is a Hollywood costume designer and chief designer for Orbital Outfitters. He has an array of spacesuits he's designing for the company. His passion for accuracy in his costumes eventually landed him a real commission with NASA to design a woman's upper torso spacesuit.
While looking at real suits very close up, you start to understand that they're not just a white jumpsuit with plastic fittings and a bubble helmet. Think of a spacesuit as a personal spacecraft.
To protect the body, spacesuits are designed in layers.
Imagine the kind of clothes that you'd have to wear if you were walking through the Sahara on twice its worst day ever, and then make one more step and you're into the Arctic. That's the kind of clothes you have to wear.
And when considering the form and function of his Orbital Outfitter suits, Gillum looks back in time to medieval armor to help create future designs.
Here is our 14th century hourglass gauntlet. That knuckle bow is almost identical to the one that is under the fabric cover in a shuttle spacesuit glove. And interesting enough, it's almost the exact same shape as well. And it performs the same function.
While space diving might be years away from becoming a reality, thrill seekers are already making their way to the edge of space, the realm of Earth orbit. Up until 2001, the privilege of orbiting Earth was reserved for the elite few. Astronauts chosen to work in space. But that's before space tourism became a reality.
One of the dreams of most of the people associated with the spaceflight world is to actually fly themselves. And so space tourism has been an important component in people's thinking about spaceflight from the very beginning.
Right now, Space Adventures Limited is the only company delivering that dream.
We are the world's only private space travel company.
Space Adventures started 10 years ago when its first client took a very high-altitude ride on a Russian jet.
When he came back and talked about what it was like to see the curve of the Earth and the black sky above, I knew that we would have a great business and there would be literally millions of people out there in the world who wanted to participate in Space Adventures experiences.
Then, in 2001, American investment manager and multimillionaire Dennis Tito approached Space Adventures about arranging a trip into Earth orbit, and the era of private space tourism was born.
The flight of Dennis Tito to the International Space Station was an enormously significant accomplishment, and many people watching in the space community cheered. They thought this was great. It's a new age that has begun.
I love space.
Space Adventures Limited now offers trips to the International Space Station for $33 million.
You'll learn about the rocket. You'll learn about the spaceship that you're going to fly in. You'll learn about the space station. You'll learn about what it's like to live and eat and work and even go to the bathroom in space.
To get to the space station, space tourists must hitch a ride with the Russians in a Soyuz capsule.
It's flown successfully for 35 years. This great feat of human engineering will deliver you from the ground to orbit in less than 8 minutes.
Once delivered to the space station, space tourists live like real astronauts.
Comfortable is a relative term. So if you're comfortable on a camping trip, then you'll be fine on the space station. And if you're at all used to being in the outdoors where you don't have all the comforts of home, then you'll be quite comfortable living in a spaceship.
The food is great, but you're not going there for the food. The real enjoyment of space is being able to float weightless and see the Earth and be really part of the future of space exploration. And being able to see what it's like to step off the planet and go somewhere that very few people have been before. You'll be seeing the Earth in all its glory and splendor. You'll be watching 16 sunsets and sunrises every day because you travel so fast around the Earth.
Right now, taking a trip to space is too expensive for most private citizens.
If you were to just go in low Earth orbit around the Earth, that would cost about $10,000 a pound. That's your weight in gold.
There are many companies currently designing new spacecraft to make space travel affordable.
I can't tell you when it will be $4,000, but I can tell you it'll never be $4,000 if it doesn't start off at $40 million.
Regardless, Space Adventures Limited has big plans to expand their offerings in space.
One of our future clients will be undertaking a spacewalk for the first time. Additionally, we're very excited about our circumlunar flight program and doing a flight around the moon. They will come literally within 100 kilometers of the lunar surface.
Sending private citizens into space has changed the paradigm for space exploration.
We've really, I'd say, banged down the door for the rest of the industry. There are many people now who are interested in opening up this frontier and doing it privately, and we hope to be seen in history as the catalyst which really motivated that entire industry to begin.
Perhaps the most exhilarating part of a space adventure is getting to the edge of space. But space is a big domain, and there are threats here that are unlike anything we have on Earth. Earth orbit, our edge of space, is generally divided into 3 parts. Low Earth orbit is an 1,100-mile wide belt that is closest to Earth's atmosphere and begins only 120 miles above sea level.
There are tremendous advantages to low Earth orbits. First of all, most of the manned space program takes place in that radius.
Start 1, 0, and liftoff of Space Shuttle Endeavour.
Also, spy satellites, communication satellites, weather satellites occupy that low Earth orbit.
Low Earth orbit is like a busy city, lots of activity. The Hubble Space Telescope and the International Space Station call low Earth orbit home. Soyuz and the Space Shuttle complete missions here. Objects and people in low Earth orbit can travel around Earth in an astounding 90 minutes.
45 minutes on the sunny side of Earth, 45 minutes on the dark side of Earth.
Houston, you're go for landing, over.
Except for a few trips to the moon, all of humankind's visits to space have been to low Earth orbit.
The bottom line in low Earth orbit is if you can't reach it, you can't go anywhere else. And human spaceflight ultimately is about going somewhere else. Low Earth orbit is kind of the entry point for that effort.
Above low Earth orbit is a region called medium Earth orbit. This wide stretch of space is 1,200 to 14,000 miles above Earth. Many communication satellites are launched into orbit here, including global positioning satellites.
GPS satellites roughly orbit the Earth at about 12,000 miles, what we call a semi-synchronous orbit. So basically, they orbit the Earth twice per day, once every 12 hours. GPS is set up into 6 orbital planes. So if you can imagine a globe, there are 6 orbits positioned in equal spacing around the Earth with roughly 4 or 5 satellites per orbital plane. And basically that gives us coverage around the world.
GPS satellites sit at this altitude so that multiple satellites are in view from one location on Earth at any time of day.
It takes 4 satellites to get you your exact location. The first will give you a roundabout area, the second will refine it, as well as the third, and finally the fourth says you are exactly here.
Medium Earth orbit is also home to the treacherous Van Allen radiation belts. These belts of high-energy charged particles can send a $300 million satellite spiraling out of control, or give a human being a fatal dose of radiation. These belts stretch out from Earth like elongated rings. Satellites are carefully placed in specific altitudes to avoid these destructive belts of particles from the Sun. Even farther out lies high Earth orbit, or geosynchronous orbit. If low Earth orbit is a busy city, high Earth orbit is rural farmland. 22,000 to 35,000 miles above sea level, satellites hover above Earth, taking in an unparalleled view from a distant vantage point. Here, over 2,000 satellites call high Earth orbit home.
These satellites appear to be stationary. They make a circuit around the Earth every 24 hours, but so do we. So we have the optical illusion that these satellites are sitting there in outer space.
But in order to reach Earth orbit, an object must first leave the ground and be delivered into space. To do this, a rocket or spacecraft needs to achieve the appropriate speed and hit a target direction and altitude. Go even a few miles per hour too slow, and the forces of gravity and drag of the atmosphere will pull a spacecraft down, crashing it to the ground.
So the idea is to get out of the drag of the lower atmosphere, beyond all that turbulence and friction, and then start racing for the right direction and speed after you get up above the sensible atmosphere.
And there's a very good reason why spacecraft launch straight up rather than at an angle like an airplane.
So what typical space launches do is go straight up through the atmosphere to get through the thickest part initially, and then they begin to arc over a few miles up and then start to increase their velocity in the desired direction.
To reach a target orbit, a spacecraft must travel 17,500 miles per hour and follow a specific trajectory from the ground to desired altitude. Even 1 degree off, and a spacecraft will end up in the wrong orbit. After an 8-minute ride and millions of gallons of fuel burned, a spacecraft is now in orbit. An orbit is a reoccurring path around another object. Like Earth revolving around the Sun, a satellite or spacecraft is held in orbit by gravity. Earth's mass creates a gravitational force that deflects an object's path from a straight line. It might be assumed that Earth's gravitational pull loses much of its influence this high in the sky. But in low Earth orbit, Earth's gravity is only 2% less powerful than it is on the surface of the planet.
The way you stay in orbit is to go at a high enough speed or velocity that you are falling back to the Earth, but you're going so fast that your curved path actually never strikes the curved surface of the Earth. You just keep falling around the world over and over again. So you're not leaving the gravity behind, but you're being spun around the planet by gravity. It's what's holding you in this circular path around the planet. and it's making you fall back to Earth.
In theory, objects can stay in orbit forever, as long as they have enough speed to resist the pull of Earth's gravity. There are two types of orbits, circular and elliptical. Circular orbits are for satellites or spacecraft that need to maintain a consistent altitude and travel in a regular circle around Earth. Mapping satellites, GPS, and weather satellites all use circular orbits. Elliptical orbits are oval in shape. They're used when a high altitude is needed for part of the orbit, without having to go all the way to high-altitude circular orbit. Spacecraft delivering satellites into high orbits use elliptical orbits to deliver their payloads. Whether traveling in a circle or an elliptical path, there are many things in Earth orbit that are dangerous. In October 2007, the U.S. Navy shot down an out-of-service satellite with a cruise missile before it re-entered the atmosphere. The reason? The satellite carried hazardous material on board, and had it crashed to the ground, could have poisoned thousands.
That hazardous material was 1,000 pounds of hydrazine, which is a standard propellant.
The operation was called Burnt Frost, and it was the most elaborate effort thus far to protect the world from a serious yet growing problem called space debris, or space junk.
Space junk is anything that's man-made that was put into space and is no longer functioning. Oh, we've got junk that's been up there for as long as we've been in space.
Like a junkyard slowly becoming cluttered with debris. From the first launch of Sputnik in 1957, debris has steadily been accumulating around planet Earth.
50 years into the space race, we have littered the heavens with our garbage.
And now, about 20,000 pieces later, Earth orbit has turned into a deadly debris-filled junkyard.
It looks like the Earth surrounded by a hive of bees.
Most of the space debris includes shards of rockets, satellites that no longer function, or pieces of an object that have broken up after a launch. Caught in Earth's gravitational pull, these pieces are traveling upwards of 22,000 miles per hour.
Say more than 10 times faster than a bullet.
A collision between functioning objects such as satellites or inhabited spacecraft and space junk could be catastrophic. The Joint Space Operations Center, or JSPOC, is a top-secret Air Force surveillance unit that makes it their business to track every object that orbits around Earth, including space debris.
We use a number of different sensors around the world, known as the Space Surveillance Network. It's a network of 29 stations all around the globe, radars as well as optical telescopes that track over 18,000 man-made objects in space. And that includes active satellites as well as dead satellites, and then rocket bodies that were associated with those launches, as well as debris, things that have just shed off. If they were to run into each other, it really would be a catastrophic conjunction.
To be tracked by JSPOC, debris must be at least 2 inches wide. There are much smaller objects that cannot be tracked.
On most of my shuttle flights, we always saw small pits in the windows about the size of a pencil point.
The highest population of debris are in low Earth orbit.
And in 2008, an intentional collision between two satellites created an international outrage and a cloud of debris that threatened low Earth orbit like never before. Our edge of space is Earth orbit, a new frontier for space tourism and exploration. But danger lurks here, space debris, and it threatens our spacecraft and satellites like never before. In 2007, the total estimated amount of space debris was 20,000 pieces, 14,000 of which were trackable. Then, in 2008, China's space program intentionally crashed 2 satellites together as an anti-satellite test. The international space community was outraged.
The 10th of January of 2007, the number of objects we were tracking was less than 14,000. Here we are 16 months later, and we've increased that number by over 30% to over 18,000.
The problem of space debris continues to grow, and collisions have already occurred between space junk and functioning objects.
One of them was a piece of debris that struck a gravitation boom on a spacecraft, severed the boom.
To avoid future collisions, JSPOC is in constant contact with NASA and other international space entities to inform them when a spacecraft or satellite might be threatened, so that the spacecraft could be maneuvered around the space debris. Much like a boat maneuvers around hazards in a waterway.
Beneath the surface of the water here, what you can't see is what's going to actually give you the most damage if we run into a log or a snag beneath the surface. And in orbit, that's the same problem that we face. We don't track all the debris that could actually cripple or kill your spacecraft. And we rely on the fact that you're just statistically unlikely to hit a piece of debris to protect you. And that insurance policy is going to run out someday.
Fortunately, there haven't been any catastrophic collisions between inhabited spacecraft and space debris, yet.
We've never seen a human-piloted spacecraft run into orbital debris and been damaged, but we've had some close calls.
Objects, no matter what their size, are always in danger of being pulled out of their orbits by orbital decay. Orbital decay occurs when an object loses speed caused by friction and begins to be pulled towards Earth by gravity. Atmospheric drag is the major cause of orbital decay, like a bicyclist on the road.
When you're pedaling along at a constant speed, you're balancing your muscle power against the drag on the tires from the road and the resistance of the air that you're moving through. And you overcome that resistance on the bicycle with your muscles, or in space by firing your rocket engines to add a little speed and overcome that air resistance. That's what has to happen in space to keep the space station from falling back to Earth and burning up. And if you stop adding thrust, that air resistance will eventually slow you down to the point where you'll stop or fall back into the atmosphere and re-enter.
Some pieces survive re-entry. And the size of these pieces that have fallen to Earth is terrifying. In the last 40 years, 17,000 pieces of space debris have survived re-entry.
Back in 1997, we had a 570-pound stainless steel tank that landed about 50 yards from our farmer's house in Texas. He was not particularly pleased by that.
If a piece of debris does survive re-entry, it travels at subsonic speeds of 120 miles per hour until it hits the ground.
There was a re-entry that came in to Cape Town, South Africa. It was during the day. There were people out working in fields. They heard a sonic boom, and they looked up, and they basically saw this material coming down.
The Aerospace Corporation in El Segundo, California, is a facility that collects and studies space junk for the military and private companies.
This is a piece of what was once a piece of space junk. This was a part of a rocket stage that was used to put a GPS satellite in orbit. And here you can see the brackets that were actually melted off as this came down. We actually have cut samples here to try to understand what happened in this area, how hot did it get, and we use that information to improve our models.
Understanding how these pieces survive re-entry is important for future spacecraft and satellite construction. Recovering and reusing critical spacecraft parts could save millions in manufacturing costs. However, collecting space debris remains tricky.
3/4 of the Earth's surface is water, so a lot of it lands in the water. So when you find a piece on the ground, it's actually a very rare event.
It's estimated the amount of space debris will double by 2050. But that hasn't deterred entrepreneurs who continue to explore Earth orbit as a business location. For a mere $2,500, Memorial Space Flights, which began service in 2008, will launch ashes of a loved one into low Earth orbit. It's a fitting end to anyone who dreamed of one day visiting outer space. This is just one of the many ideas entrepreneurs are developing for Earth orbit. But to run a business in space, there needs to be a way to obtain permanent occupancy.
Here we are in the early years of the 21st century, and I foresee space becoming an industrial park.
Skylab, Mir, and now the International Space Station have all provided an arena for long-term habitation and experiments in space. What if private companies could also have spacecraft orbiting the Earth?
I think we were and are the first company to have deployed that kind of structure.
Just off the Las Vegas Strip, Bob Bigelow and his team at Bigelow Aerospace are hunkered down in a high-security facility creating a new generation of spacecraft.
I'm living out a childhood fantasy is what it is. And I think that we are involved in something really important.
Private industry is exploring the opportunities of our edge of space. Bigelow Aerospace is developing inflating workspaces called Genesis to launch into Earth orbit. The technology was inspired by NASA.
I came across an article about a technology that NASA had been working on, and I thought, oh my God, this is great.
NASA developed an inflatable module, a room called the Transhab, that was going to be joined to the space station to provide more living space. NASA was never able to afford executing that plan.
Eventually, after a number of years, we acquired the licenses from NASA for their patents.
The concept is ingenious. Bigelow spacecraft are inflatable pods that tuck into the nose of an unmanned rocket during launch, then expand to 3 times their travel size to full capacity once released into orbit.
In a rocket fairing, you only have so much volume, so much room. Like this bottle. That's as big as it gets, that's it. But if you launch something in that volume that can later expand to 3 times its size, you have a lot more room to do something with.
We use compressed gas to expand it into its form.
The inflatable spacecraft can be adapted to whatever a client might need. Research laboratory, manufacturing facility, hotel space, all emerging industries for Earth orbit.
We can host a variety of different kinds of clients, and they only have to pay for the specific time that they're interested in.
The spacecraft is assembled from very durable but bendable materials called soft goods systems.
You've driven all your life on soft goods. You've driven on tires. The inflatable systems can be extremely reliable and very strong.
Bigelow's not worried about the reliability of his launch system. The Kepler-18 rockets he's using are the same ones the Russians trust with some of their most precious payloads.
They have about 1,100 of those rockets with nuclear missiles on them right now. We're not going to fail because the rocket failed.
Once in orbit, instrumentation is powered by 4 solar panels, just like the International Space Station. The Genesis spacecraft is a new generation of space station, and it might be a vast improvement from the government issue brand.
What we're working on, if we're successful, is a much safer vessel for humans to be in than the aluminum cans are.
Our inflatable hull structure is adequate to protect against any type of thermal effects, micrometeoroid protection, radiation effects.
Bigelow Aerospace now has 2 private spacecraft, Genesis 1 and 2, orbiting 340 miles above Earth. The only privately owned spacecraft of their kind orbiting in the edge of space. Launching spacecraft into Earth orbit is only one challenge. Picking an appropriate inclination for its orbits is another.
The orientation of an orbit really is just a measure of the degree of tilt from the line running through the equator. You can have anything from 0-degree inclination to 90-degree inclination. The 0-degree inclination is absolutely no tilt whatsoever from the equator, and that is called an equatorial orbit. Whereas if you have a 90-degree tilt from the equator, that is the polar orbit.
Satellites and spacecraft are launched into different inclinations depending on their mission, because different inclinations pass over different parts of Earth.
If you're going around the Earth, around the equator, what do you get to see? It's just what's below you, which is going to be what? The equator. So an inclination of the orbit at, say, 56 degrees covers almost all of the population of the Earth.
A polar orbit satellite has the ability to view the entire Earth in a few orbital rotations. As the Earth slowly rotates below, the satellite keeps sweeping overhead, allowing the entire Earth to be observed in a short period of time. If the mission is for espionage or observation, sun-synchronous orbits allow satellites to pass over the same point on Earth at the same time every day. They shift 1 degree each Earth day to stay in sync with the sun at a given location. If constant communication is necessary, geosynchronous satellites are positioned far away from Earth so that entire continents are within their view.
It matches the rotation of the Earth and appears to hover in the sky. It's a very useful trait of that orbit because you can then stay constantly in radio or television touch with the spot on the ground below.
Earth orbit is the natural extension of Earth's occupation in space. And if future plans pan out, the industrialization of the edge of space will happen in the near future. It was only 40 years ago John Glenn entered Earth orbit. What the next 50 or 100 years holds for the future of Earth orbit is as exciting as perhaps a walk on the moon once was to an older generation. Bigelow Aerospace has already reached a major milestone by launching their Genesis 1 and 2 pods into orbit. But future spacecraft will be ready for private citizens.
Nobody's done this before. I mean, people have gone to space, but what we're trying to do is make it available.
It's called Sundancer, a 300 cubic meter inhabitable space that will have the capacity to support up to 3 human lives indefinitely.
We have to add a lot of life support equipment to make sure that the environment is sustainable for a crew of 3. That goes into anything from the air concentration system, where oxygen has to be delivered, CO2 has to get removed, all the way through more rigorous thermal control and humidity control.
One Sundancer spacecraft offers more space than is currently available on the entire International Space Station. Eventually, multiple pods will be connected together, like Tinker Toys, for larger facilities.
What kind of shape you're choosing depends on the purpose, the mission for the spacecraft.
But like pioneers setting off across the open sea in search of new land, this is uncharted territory.
We have an opportunity to turn that vision into a reality. And so far, that's exactly what we're doing.
They are one group of many that dream of permanent occupancy at the edge of space. One thing remains clear. Earth needs an easy way to deliver spacecraft, cargo, and people into space to take advantage of Earth orbit. And the ideas are spectacular.
There have been all kinds of concepts, like space elevators.
How about a space fountain? A highly energized wave of particles that lifts cargo up into Earth orbit.
The key is finding a cheap way to get those materials up to space.
Or perhaps the resources of space can be mined in a facility orbiting Earth.
Using the resources that are on the moon and the asteroids nearby to build things in space themselves, not have to spend the money to haul them up from the ground. For example, Lewis and Clark, when they went across the continental US, they didn't haul all their drinking water and firewood with them from St. Louis on the way west. They used what they found along the way.
Earth orbit's greatest gift might be sustainable power. Imagine an array of solar panels that generates enough power to light up a continent.
That's probably one of the most promising avenues to pursue in the next 50 years in space, is to find a way to make cheap solar collectors and then build the collecting antennas on the ground so that we can use inexhaustible solar power to reduce our reliance on the finite supplies of fuel and energy we have here on Earth.
One thing is certain. The edge of space is the entryway to future exploration, a stopping point to the destinations across the universe.
I'm very excited about a future, decades from now, where the Earth really is the Garden of Eden of humanity, where we've taken care of our planet, our parks, our enjoyment, the things that we love about the Earth are taken care of. And all the things that we do in terms of manufacturing and resource extraction and energy and mining, those things take place in space.
Is there another Earth in the universe? It's perhaps one of the oldest ideas since mankind was able to look up at the stars and wonder.
Back when people were sitting around their campfires and looking up at the stars and imagining them as other campfires with other tribes around them.
What exactly do we mean by another Earth? It should support Earth-like life.
When you boil it down, life needs 3 very basic things to exist. It needs a liquid medium of some sort to do its chemical reactions in. And we think water is the most likely liquid medium. It's very prevalent in the universe. We also need to look for the basic building blocks of life, the molecules that can help to put life together, the phosphorus in your DNA, and we need to have an energy source. It turns out that a terrestrial planet that has water on it pretty much has all of those things we need.
Not all planets capable of supporting Earth-like life would have to be carbon copies of our own Earth.
So you can think of it like a series of different types of houses. If you go into a city, for example, there will be grand mansions, and there will be smaller, more modest little two-bedroom homes, and there'll be city studios and skyscrapers and so on and so forth. All of these house people, all of these can help house life. And so we think about that when we go out into the universe looking. We're going to be looking for houses of all different kinds and keeping our minds open as to what could support life.
Astronomers have found over 300 exoplanets, that is, planets outside our solar system. The vast majority are gas giants, which are easier to find than small terrestrial planets like our Earth.
To build instruments to analyze those Earth-like planets, we have to anticipate ahead of time what the chemicals might be in that Earth-like atmosphere. For that reason, we need theory, we need models.
Victoria Meadows is in the planet modeling business. She heads up the Virtual Planet Laboratory at Seattle's University of Washington. The group, spread across institutions around the country, builds worlds that may exist in the yet unexplored universe.
The Virtual Planetary Laboratory allows us to simulate what planets might look like from space and what their environments might be like in advance of actually discovering these things out there in the universe. So it allows us to explore what planets might be like.
In the Virtual Planet Lab, fantastic worlds can be built, like a science fiction novelist with a supercomputer as a writing partner.
So we can take something that's like the Earth, but we whip away the sun, and we replace it with a star of different size and temperature. So what we've done with the Virtual Planetary Laboratory is modeled planets that started out as Earth-like and put them around stars that were much hotter with much stronger UV radiation, for example, than our own sun.
The models can produce bizarre alternate Earths filled with plants that are bright red, orange, or even pitch black. Photosynthesis can vary greatly depending on the light of the star that's shining on it.
Planets around F stars, for example, where the light from the star is much bluer, the plants there will tend to absorb more blue light, and so those plants could potentially be more likely to reflect red, orange, and yellow light, and so will appear red, orange, and yellow to us.
Plants on a world around weaker stars could evolve their coloration to use every bit of energy falling on them.
If you go down to much cooler stars than our sun, to M stars, plants on planets around M stars might in fact be black because they want to absorb as much light as possible to do their photosynthesis and to feed.
And then there's the water world planet, a theoretical Earth circling a volatile M-type star that constantly hits the planet with outbursts of deadly radiation.
And how does life cope on the surface of that planet? Is it possible to have life even when you have a flaring M star? It turns out that you can actually live about 9 meters underwater on a planet around an M star and still escape the worst of the flares, but still have enough light to be able to do photosynthesis and to survive.
Everything looks good from here.
And as future exploration missions are being drawn up, many scientists are focusing on what it would take to detect the byproducts of life on a distant planet.
Life produces gases. Life stinks. You can smell it. And we're going to look for those gases with these high-resolution spectrometers.
So what we really need to do is take the light from another Earth-like planet and analyze it to find out what the chemical composition of that atmosphere is.
Finding the locations of planets is something that UC Berkeley astronomer Jeff Marcy is very good at. He and his astronomy colleague, Paul Butler, are credited with finding more exoplanets than anyone else.
A planet that's farther from its host star will be very cool. And so there's a domain in between that we sometimes call the Goldilocks zone or the habitable zone, where the temperature is just right. And by just right, I mean lukewarm, so that water would be in liquid form. And of course, it's liquid water that's the prerequisite for life.
When we look at other planets and we ask, could there be life on other planets? My first question is, could that planet support liquid water? Yes, I'm interested. No, I'm not interested. It all comes down to show me the water.
Water is an amazing substance. We are frankly fortunate that the universe has something called water. It's the great cosmic cocktail mixer. Water is the critical stuff that allows the chemical reactions to take place that eventually lead to life.
But this special zone, where liquid water can exist, varies from place to place. If a star is a hot O type, the zone will be farther out from a sun. If it's a cool M type, the zone will be closer in. And it even changes with time. Stars are not stable. Even our own comfy habitable zone here on Earth will change in a few million years when our sun grows older and much hotter. Current technology doesn't exist to take pictures of distant exoplanets. So astronomers use the solar system star as a sort of proxy for a planet, since both were formed from the same planetary disk of material.
How do we know what a star is made out of? We don't go there and sample it. Your experiment would melt.
Astronomer Wes Traub heads up the effort by NASA's Jet Propulsion Laboratory to come up with the next generation of instruments that will look at planets outside our solar system.
What we do is we just simply look at it and we break the light up into different colors. This was done several hundred years ago by Newton. He discovered that if you put a prism in a ray of sunlight, it breaks it up into blue, green, red. And you look at these different colors and you discover something very startling all of a sudden. There are parts where colors are missing, and these missing colors are a fingerprint of the constituent of the sun that you're looking at.
With current technology, we can't directly view a spectrum of a planet outside our solar system. But eventually, more powerful instruments will allow us to use the same technique to fingerprint a planet for evidence of life.
If we look at that light from the planet and break it up with a prism or something similar, we can tell what the planet is made out of, and that's how we know whether our planet has oxygen, like our atmosphere, whether it has water vapor in the atmosphere, whether it has ozone, carbon dioxide, and nitrous oxide.
But nothing in the universe stays the same over time.
When our Earth formed 4.5 billion years ago, it had a very different atmosphere than it has now.
It's a challenge that Meadows and her team anticipate as they build their models of other Earth-like planets.
We would be very short-sighted to look just for an oxygen-rich planet at the same stage of development. So the thing is, when we go out to look for habitable worlds, they could all be extremely different. They could be very diverse.
And if we find another Earth, what are the chances we'll find a civilization on it that we can communicate with? What's the number of intelligent civilizations that might exist on other Earths in the universe? What would have to go into such a calculation?
How many stars are there? How many of those stars have planets? How many of those planets are close enough to have water? And on and on.
That's a problem that astronomers Carl Sagan and Frank Drake took on decades ago. Drake came up with an equation that estimated that up to 1 million civilizations may exist in just our Milky Way alone.
The Drake equation is this series of numbers that are trying to be put together in such a way to give us a kind of way of even closely estimating how many other intelligent civilizations are out there.
Peter Ward, a professor of biology and geology at Seattle's University of Washington, thinks the Drake equation greatly overestimates the number of advanced civilizations that could exist on other Earths in the universe. Ward and astronomy professor Don Brownlee's book, Rare Earth, explains why they think complex life, animal life like humans, may be rare in the universe.
We began to think that it was just too simplistic, that there's other stuff involved.
Ward cites a number of factors that he thinks would lower the original Drake estimates of how much complex life could exist in the Milky Way, and by extension, the universe.
First of all, plate tectonics. Plate tectonics is continental drift, and one wonders why would that have anything to do with the frequency of life on the planet? Plate tectonics also produces a recycling of elements, and that recycling does some very fundamental things. The most fundamental thing it does, it produces a temperature gauge. It's like a thermostat on the planet. If we get too warm, plate tectonic processes help us cool off.
Then there's the presence of metal on the planet.
Secondly, if you want to be an intelligent civilization, you better have metal. Metal's hard to find on a planet like Mars or Venus. But plate tectonics rotates everything, causes cracks, up come the heavy metals. What else do we need? We need a good Jupiter.
Having a gas giant like Jupiter, with its strong gravitational pull and the outer reaches of a solar system, protects the inner planets, those potential Earths, from frequent catastrophic impacts.
And the reason is those Jupiters sweep up gravitationally the asteroids and the comets, flinging them away, allowing the Earth to survive without so many impacts by that debris. And so it's those protective Jupiters that allow life to proceed without impacts by these asteroids and comets that would cause mass extinctions, as indeed happened to the dinosaurs.
65 million years ago, an asteroid hit Earth and wiped out most of the dinosaurs on the planet.
Those dinosaurs went out because Jupiter failed on the job and should have been fired. Bad Jupiter that day. It let one of these asteroids sweep by, but we've seen what it usually does. Comet Shoemaker-Levy that smashed into Jupiter at the last part of the last century. That's what Jupiter generally does. So good Jupiters are good things to have, and you can make equations for this.
When considering the habitability of planets, most astronomers place great emphasis on finding worlds in the habitable zone around a star. But Ward and his co-author believe that a planet's position within the larger galaxy is also critical.
So that's why we have defined, or did define, something we call the galactic habitable zone. That area within a galaxy, not too close, not too far. It's a Goldilocks area within our galaxy that's just right.
They came up with 9 factors that make up a so-called galactic habitable zone. Earth's position in the galaxy was considered. Away from killer neutron stars, black holes, and deadly gamma ray bursts. They included the percentage of stars that have planets and the percentage that have microbial life. They even estimated how often planets might have all their life extinguished. Earth itself may have narrowly missed such an event in 1998. Then, a high-density star called a magnetar burped out a flare of deadly gamma rays, unleashing as much energy in 0.2 of a second as the sun will put out in the next 100,000 years. Luckily, the magnetar was located 20,000 light-years away from Earth.
A really good question would be to ask, what would have happened had that magnetar that burped not been 20,000 light-years away, but 10,000 light-years away? Could there be a case where we had something within a few hundred light-years? If that were the case, new calculations suggest it could punch our atmosphere off, woof, in one burst. And you go, I can't breathe. Now that's catastrophic, and that is totally possible.
Humans may be just a cosmic fluke in the universe. The optimistic assumptions of the Drake equation may just not hold up with what astronomers have learned in the past decades.
The Drake equation was a fantastic construct, but it was done in the 1960s. We know so much more now. So we've added in stuff that wasn't known then, and I think it makes it more accurate. But ultimately, it also brings down the numbers. And the million civilizations I do not think can be supported by current understanding.
So how many other Earths supporting advanced civilizations does he think may exist in our Milky Way?
I've been asked over and over to make a prediction, and I'd say, well, we know it's at least one. It's more than one, I think. But I think it's more than one, but way less than a million.
Locating another civilization may happen as astronomers concentrate on looking for other Earth-like planets. But finding those Earths in the first place is a huge technical challenge for scientists. Unlike the stars that have been cataloged, planets can't be seen using current technology. A planet, when examined from light years away, is almost on top of its sun as viewed from outside our solar system. And to make matters worse, an Earth-like planet, even one many times larger than our Earth, reflects only an infinitesimal amount of light compared to its star.
So here we have a bright star and a planet which is 10 billion times fainter. It's hard to imagine what 10 billion times really is, but the way many of us think of this is, suppose you have a firefly, a very small firefly, a very weak light, and suppose that firefly is orbiting around or flying around a lighthouse. And suppose you're trying to look at this firefly flying around this lighthouse from 3,000 miles away. That's something what it's like.
Let's assume you could find that speck of a firefly from across the country, and then you had to figure out what that firefly is breathing by analyzing the gas it's exhaling. That's the challenge that faces an astronomer who first has to find a planet, then figure out how Earth-like its atmosphere is. But astronomers have figured out indirect ways to find extrasolar planets.
If that were the star, and very bright, and this were the planet, and it moved in front of that star, the star would get dimmer, and you would notice that.
It's called the transit method of discovering a planet, since it depends on seeing the travel or transit of a planet across a distant star.
The amount of light it blocks when it's in front tells us how big the planet is. So we use that to understand whether it's a small planet like Mercury, a planet like the Earth, or a huge giant like that of Jupiter. And we use the orbital period and the temperature of the star to tell us if it's in the habitable zone.
The orbital period is how long a planet takes to go around its star.
Then it would go on its way and come back again a year later and do it over again.
When that period is combined with the type and size of the star, the information will tell scientists if the planets that are found are potentially in a habitable zone. The transit method works if the observer or the telescope is in the same plane as the star and its planets. But if you're above or below the system, another technique called the radial velocity method might be used. That method depends on careful observations of a distant star to watch if it's being gravitationally tugged back and forth by an unseen exoplanet. Astronomers can use that information to figure out details about the exoplanet that's influencing the star. Equipped with these tools, astronomers are finding hundreds of planets, some never dreamed of in astronomy textbooks. Super Earths, hot Jupiters, and even some close cousins to our own Earth. In the search for other Earths in the billions of stars in the universe, astronomers have found a relationship between the composition of a star and the probability that it may have planets, both Earth-like and otherwise.
The stars that have heavier elements in them, the iron and the nickel and the silicon, have heavier elements for a good reason. Those stars formed out of molecular clouds in the Milky Way galaxy that collapsed down to form the star, and in so doing, left some placental material around them that eventually coagulated into the planets. So it makes sense that stars that formed with lots of heavy elements will form planets that also have lots of heavier elements.
Astronomers call the proportion of heavy elements in a star its metallicity. But that doesn't necessarily mean it has a lot of metal in the conventional sense.
Metal, for an astronomer, is any element that's heavier than hydrogen or helium. So in astronomer speak, lithium is a metal, sulfur is a metal, chlorine is a metal, and not just elements like iron, gold, and silver.
An Earth-like exoplanet not only needs heavy elements in its composition and to be in a star's habitable zone, it also needs to be the right size to sustain life. Right size means it can hold on to its atmosphere and have plate tectonics and volcanoes, both considered critical to regulating a planet's temperature. To do all this, astronomers estimate that the smallest a planet can be is 1/3 of Earth's mass. On the high side, a habitable planet cannot be greater than 10 times our Earth's mass. The very existence of exoplanets has gone from theory to reality only in the last decade.
A little over 10 years ago, we had no known extrasolar planets at all. The only planets we knew of were those orbiting our sun. And now we know of planets orbiting other stars. And of course, what's really exciting about these planets is that some of them may be habitable, and so there's a chance that there's life on some of them.
Of the hundreds of exoplanets found, some may not follow the familiar blueprint of planets in our solar system.
We found these bizarre Jupiters that orbit very close to their star. They're blowtorched hot, and these Jupiters undoubtedly got close to their star by migrating inward.
Sometimes the formation of a Jupiter-mass planet can be kind of a death knell for terrestrial planets in the system.
And what if we had been unlucky enough to have such a Jupiter in our solar system?
It would have slingshot the Earth right out of its orbit into the vast cold darkness of outer space, and the Earth would eventually die off as a cold, dark hulk.
Over 300 exoplanets have been discovered, and more are being found all the time. But the majority are monstrously huge gas giants that hold little promise of being truly Earth-like. In the Pegasus constellation, some 50 light-years from Earth, the planet 51 Pegasi b can be found. It was the first planet discovered outside our solar system. A gas giant as big as Jupiter, but orbiting much closer to its star. It races around its sun in just 4 days. The planet 70 Virginis b is even farther away than Pegasi, at 60 light-years. It's 7.5 times as massive as our Jupiter. At first, it was believed to be in the habitable zone of the star, so it was nicknamed Goldilocks. Later calculations showed that it had an eccentric orbit that brought it to within 27 million miles of its sun, which is roasting hot. so it's no longer considered to be in a habitable range. The massive gas giant Trace 4 is over 1.5 times the diameter of our Jupiter, making it the largest planet found so far. It's 1,400 light-years from Earth. This gas giant, even though it's much larger than Jupiter, only has a little over 3/4 of its mass. It's a hot Jupiter, zooming around its sun in only 3.5 days. Astronomers haven't been able to find true Earth-like planets outside our solar system because they've not yet been able to detect such relatively small rocky planets as our Earth. The technology is just not there yet. But astronomers are having more luck finding what are termed super-Earths.
People actually being able to discover planets that could potentially be in the habitable zone around other stars. And one classic example of this is a planet called Gliese 581c.
The Gliese 581 system is located about 20.5 light-years from Earth in the Libra constellation. Gliese 581c has 5 times the mass of our Earth. There were hopes that 581c would be the first Earth-like planet found in the habitable zone of a star, but that turned out to be wrong.
Probably it's a little bit on the wrong side of the fence. So that one, instead of being a super-Earth, is probably a super-Venus.
It's like our own Venus, way on the hot side, with possible 600-degree temperatures, but also more massive than Venus. But Gliese 581c has a relative a little farther out and cooler. It's named Gliese 581d.
And this one is at the far back end of the habitable zone, where it's quite cold. When you initially look at it, you think, well, maybe that's a bit too cold. But it turns out that if the planet potentially has enough greenhouse gases, it might be possible to make that planet warm.
Another promising Earth-like planet may be HD 69830d. This is a big planet, 17 times the size of our Earth. It's about 42 light-years away from our solar system in the constellation Puppis.
HD 69830d is a potential planet where life could form because it has approximately the right temperature.
The planet could have a temperature between that of Venus and Earth, and it has a close to circular orbit, meaning it won't get toasted by close encounters with the star it's orbiting.
So you can have liquid water. The mass of the planet is maybe not so good. It's about 17 times the mass of the Earth, which could be a solid ball of rock, or it could also be a gas ball like Neptune in our solar system.
When NASA's able to fly future planet-finding missions, it's expected that astronomers will be able to get a spectrum that will give us much more information about the composition of the planet. They may be able to figure out if the planet has a solid surface, or that it's a water world, or perhaps something else entirely. The search for other Earths has taken astronomers light years from our neighborhood in space. But could another Earth exist in our own solar system? While astronomers look at star systems many light years away in hopes of finding another blue marble of a planet, other Earths may be a lot closer than that.
So imagine going back 3.5 billion years ago and visiting our solar system. You'd have seen 2 blue marbles here. Earth, water, thick carbon dioxide atmosphere, warm conditions, life. Now imagine moving a little over, you see Mars. Water on the surface, thick carbon dioxide atmosphere, warm conditions, possibly life. Well, the 2 planets start evolving. Earth stays habitable. Mars doesn't.
Both Venus and Mars are just on the edge of the Goldilocks zone of habitability. both may be cases of failed Earths. Once you fall off that path, you may never be able to come back.
Mars is a lesson for what you need to maintain habitability for a long time. And the answer, we think, turns out to be big. You have to be as big as the Earth to maintain habitability for a long time. Mars is too small. Being too small, it has no way to recycle its elements and has no way to hold on to its atmosphere for a long time. So size matters.
And while Mars is now too cold, Venus, our other would-be Earth, has the opposite problem. It's too hot.
It was a little bit too close to its star, too close to the sun. It got hot and it stayed hot. And so all the carbon dioxide, the CO2 and so on, that formed on Earth, formed also on Venus. But on Earth, it was incorporated into rocks. On Venus, it stayed in the atmosphere. And the atmosphere basically is global warming to the nth degree. Sunlight comes in and it just doesn't leave. That planet is like the inside of a pizza oven.
Venus failed because it was born in the wrong place. Mars failed because it was born the wrong size. So we have an interesting story here, Venus, Earth, and Mars. Venus is in the wrong place, Mars is the wrong size, Earth is the right place and the right size.
So if the planets in our solar system aren't great candidates for being Earth-like, our closest galactic neighbor, Alpha Centauri, may harbor an Earth-like planet. At a little over 4 light-years away, in galactic terms, it's next door.
I think that there's a good chance that Earth-like planets are orbiting around either one or both stars in the Alpha Centauri system.
Astronomer Greg Laughlin has done computer modeling to show that Earth-like planets should exist in the system.
There's a number of reasons why Alpha Centauri is the best star in the sky for hunting for Earths. Alpha Centauri is very close by. Alpha Centauri has 2 sun-like stars. Alpha Centauri has a large quantity of the kinds of heavy elements that go into building planets.
How close is the Alpha Centauri system to us? First imagine shrinking our sun down to the size of a grain of sand.
A grain of sand is just about the smallest object that you can see with your eyes and just about the smallest object that you can actually feel with your fingers. And at the scale where the sun is the size of a grain of sand, the Alpha Centauri system is 3 more sand grains placed about 5 miles away. Now, if we wanted to get a similarly good system to Alpha Centauri, we'd have to actually go all the way over the horizon and find another stellar system that's good.
And it turns out that the stars of the Alpha Centauri system should have plenty of raw materials to make planets out of.
Alpha Centauri has a higher metallicity than our own sun does, and that implies that planet formation was a process that took place relatively easily in that system.
And last but not least, Alpha Centauri's 2 main stars provide an additional benefit.
The initial indications show that there are no Jupiter-mass planets in the Alpha Centauri system. That makes it more straightforward for terrestrial planets to form around either or both of the stars.
That's because large gas giants form around cores of ice that are as big as our entire Earth. So these giants need a lot of cold space to form these cores. Think of how far out Jupiter is from our sun. However, when you have 2 stars with overlapping orbits in a system like Alpha Centauri, there isn't a space in the system that's big enough and cold enough to allow the formation of these gas giants.
So we expect that the planets that exist in the Alpha Centauri system, if they're there, they're terrestrial planets like the Earth or Mars or Venus. They're not gas giant planets like Jupiter or Saturn.
What if we could actually survey how many Earths are in our part of the universe? What if we could peer directly into the atmosphere of another Earth that was light years away? In order to find another Earth, astronomers have to eventually overcome the huge technical challenges of how to view a distant planet. It's a problem that NASA has tackled much like the race for the moon, with plans that stretch out over decades. The first exoplanet-finding mission will be Kepler, which launches in 2009. The NASA survey project is named after the 17th century astronomer Johannes Kepler, who discovered the laws of planetary motion.
What Kepler will do is so utterly simple and yet extraordinarily powerful, it brings tears to my eyes. What Kepler will do is simply be a space-borne telescope and stare at the constellations Cygnus and Lyra, taking picture after picture after picture, with the goal of looking for stars that dim when an Earth-like planet blocks some of the starlight. And it will be the first time that we humans detect other Earth-like planets around other stars.
The principal investigator for Kepler is William Barucki. He's been championing the mission for 25 years.
Kepler basically is a space mission that puts up a very large telescope. It's very much like a camcorder. It's always taking pictures of these stars, sending that information back to you.
The mission is a comparatively small survey project to look at a fixed portion of the sky for an initial time of 3.5 years.
The main result from Kepler will be to give us a statistical count. It's a head count of what the population is. You know, how many small planets do you have and how many large planets do you have?
Kepler's results will in turn be used to help decide what will be built for the next generation of planet-finding missions.
Kepler really is one step along the way. It's to try to find Earths and find out whether they're frequent. If they are frequent, they must be close, so we can build a modest instrument. If we don't find many Earths, what that means is before you're going to find another one, you're going to have to look a huge distance into space. So you're going to have to build a much bigger, much more expensive instrument.
The most majestic, spectacular telescope ever conceived by humanity is something called the Terrestrial Planet Finder. It will be an enormous telescope in space, frankly probably costing several $1 billion, but what it will do is absolutely unique. It will be the first telescope to take pictures of other Earth-like planets.
To directly view a planet outside our solar system, a whole new telescope technology is being developed.
To construct the Terrestrial Planet Finder that will image Earths against the glare of their host stars, we need some entirely new optical technology. A technology that, frankly, we haven't invented yet. The frustration is just palpable that we actually know vaguely how to detect other Earths, but we don't know exactly how to build the optics to do so.
NASA envisions the Terrestrial Planet Finder as a suite of two very different but complementary advanced concept telescopes. The first, the visible light coronagraph, consists of a large optical telescope with a mirror at least 100 times more precise than the Hubble Space Telescope.
A coronagraph is a single telescope which collects the light from a star and focuses the light at the back end like a normal telescope. Except at that point, we block the light from the star and we try to let the light from the planet come through. By doing this, you cancel out the scattered light in the instrument, and so you allow yourself to be able to look at this planet which is 10 billion times fainter than the main star.
The second Terrestrial Planet Finder mission will be an interferometer.
An interferometer works by taking the light from a star that comes in and capturing it with 2 telescopes, sometimes more. And this combined light can be arranged in such a way that the light from the star disappears. That's good in the sense that you now can look at the planet that's next to it, and the light from the planet does not disappear. That's the magic of an interferometer.
To get all this done, new levels of precision in control and command technologies need to be perfected. Something that could take years to develop. The quest for the holy grail of astronomy, another Earth outside our solar system, has pushed scientists to speculate about how such a discovery could affect us.
I think if we find another Earth out there, that's going to have an enormous impact on society. I think to know that we are not alone, that we are one of many potential sites for life, I think will cause a huge paradigm shift in people's thinking.
But there's also the possibility that we may be unique in the universe, and that we may well find Earth-like planets, but no intelligent beings on them.
We have to remember something a little sobering. It is still possible that we humans are some fluke on the evolutionary tree, a twig, if you will, that happened on the East African savanna 2 million years ago, and those hominids somehow occupied a very rare niche that hadn't happened in 4.5 billion years on the Earth. It could still be that we humans are an extraordinary rarity in the Milky Way galaxy. In fact, it could be our destiny as a species to explore the Milky Way galaxy and be the first such explorer species.